Hello Year 11, this is Mr. Tickner and this is a video that takes you through the physics mock that you sat in core paper. There are some timestamps at the bottom that allow you to jump to particular questions and we'll go through the answers and hopefully this will help make anything clear if you've still got some questions on it. So let's load this up and let's go. Right, okay, so question one, we've got a photograph. This is X-ray of an image of a person's knee. The person has had part of their knee replaced. So we've got an image, and we've got X-rays are part of the EM spectrum. State another property that all electromagnetic waves have in common. This is recall. So this is a recall sort of question. Let's make sure I get a red pen just so I can talk about this. There are two possible marking points you can put. Either they travel at the speed of light, or they travel through, or they are able to travel through a vacuum. Or you can put this sentence simply together: they all travel at the speed of light in a vacuum. Harmful effect of excessive exposure to X-rays is cancer. Simple recall. And then describe the difference between transverse waves and longitudinal waves. You may use a draw a diagram to help your answer. You can get all the marks without a diagram. The key things they're looking for is the term oscillations, and that when you're talking about transverse waves, that they are perpendicular to the direction of energy transfer or the way the wave is going. Longitudinal waves, oscillations are parallel. So writing those two sentences will get you all 3 marks. If you wanted to use a diagram, or if you were in a question that said use a diagram, so they were actually being more explicit, then you want a diagram that is fully labeled, and here's just a reminder of what they would look like. So you want a transverse wave, and you need to basically label this as being transverse. You need to label that this is the direction, and that this here, and this here, and this here in straight lines, these would be the oscillations. Okay, so that would get you 2 marks because you've mentioned oscillations, you've labeled this as transverse, and you've got the direction. For longitudinal waves, the best way is to draw a few particles and then to add just some arrows to show that they will oscillate in this plane. So and that you have again labeled the direction, and that you have said that this is longitudinal. They are very helpful diagrams to be able to draw, because you have seen a couple of times where it's been required that you use a diagram to support the answer. In this one, it wasn't required, so you could get the marks anyway. Okay, then we have our second part, where the diagram shows part of the knee. So we're on a question. This is all about, so this question is all about how to measure the mass and the volume of the bone. So first marking point is for having the correct pieces of equipment. So there's 1 marking point for saying what equipment you're using. We're going to use a balance to measure our mass, and we're going to use a measuring cylinder to get our volumes. Okay, so those 2 together, that's 1 mark. The second mark is for giving the idea of how you're going to get volume, and that is using what they call the displacement method, any method where you're going to throw it into water and see the water level rise, or catch some water that's come out of the thing called the Eureka can. So here what we've got is this. I'm saying I'm measuring the volume by putting water in a measuring cylinder and record the volume as it is, so the amount of water put in. Submerge the patella carefully under the water so no water splashes out. Record new volume and calculate the difference. So this bit here is saying that I'm doing the displacement method because I'm putting it underneath, so that gives me a mark there. I've given some additional detail. The third mark is some correct idea. So I'm calculating the difference between my initial and final volume. So I'm calculating the difference. And the fourth mark is about something that is an experimental accuracy detail. So I've put 2 in here. 1, I'm taking measurements at eye level because of parallax. I'm also submerging it carefully underwater so no water splashes out. If you sort of have your measurements and you drop your patella in from a great height, then it'll just splash a load of water out and you lose some of it. So 1 mark for your equipment, 2 marks for giving enough detail about how you get the volume, and a 3rd mark for some reasonable thing. You can say lots of things, there's loads of stuff in the mark scheme, but these are the things I would say is more obvious. Okay. Then have an equation. Obviously, you've got the formula, so this is where you get a mark for selecting the correct formula in words or symbols. So density is mass over volume. You get a mark for putting the numbers, showing that you know the numbers in, so you know which one's which is kind of nice. Another mark for getting the answer, and a 3rd mark for taking it to 2 significant figures. Okay. As with all calculations, if all we saw was 1.3 on its own, you get the marks because there's only one way to get there. Okay, question 2. This is one I want to talk a little bit more detail about. So we've got a camel and a person in the desert, and we want to describe a method you could use to find the pressure a person exerting on the ground when standing on 2 feet. And that pressure is force over area. We want to be really careful with our language. Okay, and we want to be really clear to an examiner that we're using the right word. Okay, we have to take measurements. Okay, the word calculate. Okay, does not imply you are taking a measurement. To calculate means you have already taken some measurements and you are now using a calculator. You cannot use a calculator to determine any of these things. Okay, so the word calculate is not a good word. Okay, so only use the word calculate if you are about to do a calculation. So anyway, 4 marks, 5 marking points. The first marking point is for basically recognizing that you want to use this equation. Pressure equals force over area. Expressed in words or symbols or described, but fundamentally if the examiner sees this, that gives you 1 mark. So our other marks are 2 marks are available for telling me how you get your force, 2 marks for how you get your, and 2 marks for how you get your area. So what is the force we're interested in? Well, it's the weight of this person. So the force is the weight. Okay, so I know that weight is found with mass times gravity. Okay, or mg, gravitational field strength. I should probably write properly. So therefore, I need to get this person's mass. So so I'm going to determine mass with a balance and then use W equals mg. Now that's what the marks are for. One is the idea that I'm measuring a weight, not that I'm measuring a mass, that I'm measuring a weight, because weight's the thing I need. And second is giving specific about what I'd use it. So measuring using a balance is fine. You can say a Newton meter. That's also fine. Anything that would really measure a weight is fine, or a mass. If you're measuring a mass, you then need to turn it into W equals mg. So that's what you do. The measurement of mass alone does not get you a mark here. Second thing is area. So we're interested in the area of the feet. How would I determine the area of the feet? Well, I would stand on squared paper. I draw around the foot and count. Okay, count squares for area, and that is that there are 2 marks available for that. Again, the idea of just measuring area gives you 1 mark, but describing how you would do it, there are 2. So again, 5 marking points for 4 possible marks. Just be sure to avoid using the word calculate. Okay, we then had another calculation. We're using pressure equals force over area, but before we do that, we need to turn our mass into a weight. So 1 mark is for turning weight using mass times gravity. So That's 1 mark. Second mark is for putting our numbers in. Third mark is for getting 5.1. If you forgot to do this first step, you will be out by a factor of 10. You drop a mark. It's called a power of 10 error. So that is the first step that we need to do. We need to actually do that. Right, okay. Question 3. Model electric motor is lifted through a vertical height. First, starting off with another calculation. We've got calculation. What's the equation linking gravitational potential energy, mass, gravitational field strength, and height? Gp equals mgh. Again, words or symbols is fine. And then calculate the height the load is lifted. The key thing just to be aware of with this is that we have a mass of 400 grams. We need to turn that into kilograms. So to turn it into kilograms, we divide by 1,000, which gives us 0.4, and then we can. So our first. So in order to get marks, we need to do that to avoid dropping the power of 10 error. We put our numbers in, so we substitute our numbers. We rearrange, get an answer of 0.8. If you fail to do that step, you'll be out by a factor of 1,000 and you get 0.0008, which is far less than a centimeter. So you're telling it, so it's could have been a hint that it's not a particularly realistic number, but that's where that comes from. And then this one, state the amount of useful work done on the load by the motor when the load is lifted through this height. State and 1 mark means we don't have to do any calculations. People were trying to use work as force times distance, various things. This question is just checking that do you know that work done is, the useful work done in this case is the energy that you transferred into the gravitational store. This energy in the gravitational store, that is the work done. The answer is simply 3.2 joules. And that's it. Okay, then we had a force diagram that we had to, a sort of a diagram of things. So a load is lifted at a constant speed. We've got diagram 1 shows the lifting force as it's lifted. Draw a labeled arrow to show the other force acting on the load. Ignore the effects of air resistance. So air resistance is, we don't have to worry about that. But again, what's the key information we've been given here? Constant speed. What does that mean to me as a physicist? That means that the forces are balanced. Okay, Newton's first law. There is no, the forces are balanced, so we're traveling at constant speed. That means this upwards force has to be exactly counteracted by a downwards force. Okay, and that downwards force is weight. So by I need a line that's going downwards, which is about the same length. Help if that was a straight line, which it isn't. So I'm going to draw a straight line now, hopefully. No, it's not allowing me to draw a straight line. Never mind. So it's a line of about the same length, pointing downwards, and the label for this is weight. It's not gravity. It's not, absolutely not gravity. Okay. The force due to gravity, fine, but gravity on its own does not get you a mark. Just by I, this line has to be the same length as this line. The line could also be up here, so you could draw a weight up there, up at the top, and make sure therefore they're equal, but as long as it's pointing down, weight. So our marks are for line is about the same length, and it's downwards and pointing and labeled weight. Right, then we had another equation for efficiency, joule meter. So we've got our efficiency equation. We've got 11 joules going in. We've got 3.2 joules of useful energy out because we're trying to lift things out. So efficiency is useful out over total in times 100. Stating that equation gets us 1 mark. Putting our numbers in, so 3.2 joules over 11 times 100 gets us our second mark, and we get 29. However, it is a percentage. If you fail to put the percentage sign down, then it counts it as a power of 10 error. So you need to put 29%. You need the percentage sign in order to get full marks there, because that is what you've created, you've calculated. Okay, next part of this question. Okay, So, justify why 7.8 joules of energy must be dissipated into the thermal store of the surroundings as the load is lifted. Now, this question, a lot of people misunderstood it. It does not mean explain where the energy goes. It's not asking you, so it is. So it's not where does energy go. It is not this. It's not where does energy go or how. That's not really a question. It is why. How do you know that this number is 7.8? This is the key idea. How do we know it's 7.8 joules? Two things are important. First, is that energy is conserved, okay? Or energy in equals energy out. Any idea that energy is a conserved quantity for anything. And then we are just asked basically to do a very, very simple bit of maths. We know the energy we put in. We know the useful energy out. So the stuff that's dissipated into the surroundings must be the leftover. So okay, so essentially we're saying this. Now you don't need to write down words, but you just need to have some idea. So essentially we're basically confirming that 11 joules that we put in minus 3.2 joules that we know we've accounted for, well, that equals 7.8 joules. So just showing that that's just the difference between the two things. There we go. So there was a lot of correct physics ideas in answering this question, but that weren't addressing what the question was really asking. Okay. So a Sankey diagram, complete the Sankey diagram to show the transfer of energy by the motor. I'll just say we take out things. One mark is for that idea, and the other mark is for mathematically trying to show that. Okay, so we've got a Sankey diagram. We know we've got our wasted output over here. We've got our useful energy output over here. There is one mark for having one arrow going to the right. There is another mark for the label of useful energy output. So we're matching the other things we've got. The third mark is for how wide this needs to be. And this needs to be about 8 squares. How do I know that it's about 8 squares? Well, if I think about it, if I count them up, there's 5, 10, 15, 20, 25, 26, 27. So this here is about 27.5 squares. Count over here, 5, 10, 15, 4.5. So this over here is about 19.5 squares. 27.5 minus 19.5, I'm left with 8. Now, it doesn't need to be perfect. There was some leniency given. It's meant to be about 8 by I, so the range we accepted was anywhere from 6 squares to 10 as a reasonable amount. But you don't need, there were some people did lots of calculations. You don't need to just count how many squares there are and work out how many you've got left. Okay. All right, next question. Question 4. This question is about magnets. Recall which is not attracted to a bar magnet, copper. The rest are all magnetic materials. Magnetic field lines around a bar magnet. They have this shape. They point from north to south. They don't cross. So anything that looks like this. Try not to go overboard on drawing too many lines. Just keep it simple. 4 or 5 lines is normally enough. So there's one mark for drawing one line, another mark for drawing 2 or more lines that don't cross or meet, and then a third mark for getting the arrows on them pointing the right way. Right, okay, then we have some bar magnets are made of steel. Explain why steel is a good material for making bar magnets. Well, bar magnets are permanent magnets that we want to put in a drawer and come back to a bit later. And for that, we want a thing called a hard magnetic material. So the actual 2 marks can be awarded by just literally writing a hard Okay. Now, the first mark is actually for saying that it's a magnetic material. Okay, so this bit here. Second mark is for actually saying that it's hard. What that means, okay, it stays magnetic. Okay, so it stays magnetized, remains as a magnet for a long time. Okay, so that's the aim that you want there. So you can describe what it means to have a hard magnetic material, or you can just use that definition there. We then had a Fleming left-hand rule. So draw an arrow to describe, to show the direction of the force. If you're using Fleming's left-hand rule, your second finger is pointing out of the page towards you. Your first finger is pointing upwards. That's the, that's the field from north to south. And if you orientate that, the arrow points, your thumb will point to the left. There's one mark for a horizontal arrow, either that way or that way. The second mark is for it pointing to the left. And then 2 changes you could use to decrease the magnitude of the force on the wire. The mark scheme has loads of options, but essentially they boil down to some method of having a weaker field. And you can just say weaker field, but weaker magnets or magnets further apart. Some method of having less current, so a smaller voltage or a thinner wire or anything that would result in less current flowing. So there's no necessity to talk 1 about weaker field and 2 about less current. You could take any of, there's 6 marking points, any of them are fine. So any of these points would get you the mark. Okay. Question 5, we have V equals F lambda. So we've got radio waves to detect change in material. So state the formula linking speed, frequency, and wavelength. V equals F lambda. Radio waves have a frequency of 170 megahertz. Right, okay, so this has been flagged up again. What does this symbol mean? Okay, a big capital M means mega. That means you multiply by 1 million. It does not mean millihertz, which is a little m. That means milli. And that would mean you divide by 1,000. Now, if you make that error, then you're dealing with a power of 10 error. So you'll get still 2 marks out of 3, but you'll end up with a very, very, very strange value of your wavelength. That's massively different. I think it would be, yes, it'd be absolutely enormous. So certainly with. Just be aware that you need to be happy with a big capital M means multiply by a million. A little m means divide by 8,000. So put our numbers in. You can do it in standard form, or you can do it just with typing out loads of zeros. 3 times 10 to the 8 is 300 million. 170 mega is 170 million. So our wavelength is 300 million divided by 170 million. So we get a mark for substituting, a mark for rearranging, and a mark for the answer, which is 1.8. Okay, then we have a radio wave, passes through the ground and refracts, and also has some reflection. So the wave is also reflected. Complete the diagram of 3 wavefronts after the wave has been reflected to the boundary. So our first sort of mark that generally people were happy with is you get the ray coming in, you get a reflection at approximately a reasonable angle. I've drawn a normal just to help, so I'm getting, this is my reflected angle. These wavefronts, okay, the key thing on this side is our wavefronts are going to still be perpendicular to our ray, because they're perpendicular here, they're perpendicular here, and they are going to be the same, they're going to be equally spaced as they are here. They retain this kind of spacing. So our first mark is for having a ray reflecting in kind of the right sort of way. Our second mark is for drawing things, and unfortunately this is going to be a little bit tricky because it's not snapping to a grid. So I need some things that are going to look roughly perpendicular. There's 1. There's 2. I would normally use a ruler, and there's 3. And this separation here is roughly the same as this separation here. No one's going to go and get a ruler and measure these things to the nearest millimeter, but these are much closer together. These look like that. They don't look like that. Okay? So second mark is for having 3. That's a horrible. This is why you should always use a ruler. And the third mark is for them having the same spacing as they would be there. So that's what those wavefronts will look like. Explain why the radio waves passing through the rock have a smaller wavelength than the radio waves passing through the soil. Okay, so we've got refraction from this thing into this thing, and we are bending towards the normal. So that tells us something about the refractive index of rock. So the refractive index of rock okay, we have moved into a material with a higher refractive index. That tells us that the wave, therefore, the wave is going to slow down. Now, the thing that's true of waves when they refract is, and this is something which if you didn't recall this fact, it becomes quite hard to answer the next bit of the question, is that frequency is unchanged. When waves speed up and slow down in refraction, the speed might change, the wavelength might change, but the frequency does not change. And then I can go back to this sort of equation we've got over here. Okay, and I'm just going to rewrite this equation. I'm going to take it so I make lambda the subject. So I'm going to say this is lambda is equal to V over F. So I'm going to write it. This is all I've done is divide through by the frequency without numbers. Okay, and then I can just explain. As lambda equals V over F, if V decreases and F is fixed, then wavelength will be smaller. So there is another mark for commenting on the mark scheme about the fact that the wavefronts have decreased, which is, I'll be honest, is a bit generous. But these are 4 separate marking points. Refractive index is larger, the wave slows down, the frequency is unchanged, and then you can't just quote, you can't just quote V equals F lambda. You have to explain what that means in terms of this equation. So you put it in that term. Lambda is speed over frequency. This number has gone down. This number has not changed. So therefore, your calculated answer is smaller. Okay. And that's a possible 4th marking point there. Okay, right. Question 6. Cars travelling on the road. So excellent. We've got a Doppler shift question. And this Doppler shift question, by writing the word Doppler shift, we've already got a mark. Hurrah. So we've got the car, they're going to go down, they're going to pass this person, sounding the horn, and we're interested, what is this person here, and what is this person here? Okay. The driver, okay, you can get a max with 2 marks in there, and you can get a max of 5 marks here. So you have to say something about both to get the maximum 6 marks possible. So what can we say about the driver? Okay, they are moving with the horn. Okay, so they move. They're moving with the horn. So they hear a constant frequency or constant pitch. So for them, frequency is unchanged by the driver, and they're the 2 marking points. The idea they're moving with the horn and they're moving at the same speed, just that sort of idea. So they hear a constant frequency doesn't change. That's the second mark. So there's 2 possible marks there. There's more to say about the person. Okay, so let's talk about what they're going to hear as we the key principle that this is because of is that due to the Doppler effect, they will hear to the driver. Now there's two marking points in case in that sentence. One is for recognizing the Doppler effect, and the other is for saying they are going to hear a different frequency to the driver. The key thing is you are comparing what they hear and the driver. Their frequency they're going to hear is actually going to shift as well as they listen to it. But this person and this person do hear a different frequency. So you have to compare to the driver itself. Okay, so that's two possible marking points. So as car approaches, the wavefronts get closer together. So frequency increases as car drives away. Wavefronts spread out. So frequency will decrease. Now, if we think about marking points, each of these two sentences contains two marking points. One is talking about what the wavefronts are, and then two is drawing a conclusion. So there's two marking points to there. So the thing that links all this together, which I needed, is as the speed of the waves is fixed. So in this case, we've got another link to that v equals f lambda. So what we've got here is this is a constant number, 330, must be 330, it's the speed of sound in air. If our wavelength has gone down, then our frequency must go up, and vice versa. So this also gives, if you are able to make a direct link as explaining that, then there's a mark there for that one as well. So any of these, 5 of these points, up to 2 of these points to get 6 marks in total. Okay, electricity. We have the classic thing, 4 marks for drawing a circuit diagram to get current and voltage information. What are our marks for? 1 is for correct symbols of the power supply, ammeter, voltmeter, and bulb. Okay, so those 4 together, those 4 correct symbols. Any power supply is fine, as long as it's a reasonable one. 1 mark. Second mark is that they're connected correctly. So ammeter is in series with the bulb, voltmeter is in parallel with the bulb. So 1 for the ammeter in series, 1 for the voltmeter in parallel. The final mark is for some way of changing the current and voltage in the circuit, and that's done with the variable resistor. So that's what your 4 marks are for. So symbols, ammeter in series, voltmeter in parallel around the bulb, and having a variable resistor. Okay, the arrow going the other way is perfectly fine, doesn't really matter, just as long as there's an arrow going through it. And they're your 4 marks. Okay, then they have the student results, and they say, right, okay, describe the relationship. So not explain, we're not asked to talk about the fact that bulbs get hot. Describe the results. Whenever you're describing results, saying, as thing on X happens, what happens to Y? So as voltage goes up, current goes up. That's your first mark. It is non-linear. That is a fancy way of saying it is a curved relationship. It is not a straight line. It is not proportional. So it is non-linear is the thing you want to say. Then we have a calculation, V equals IR. we're taking numbers from the graph. We know that 7 is there, so 7.2 is there. So we're asking to read basically off the graph from about here. It does allow you a bit of leeway to read up to 2.45 if you think it's slightly higher. But you end up with putting our numbers in for 1 mark, rearranging for another mark, and getting 3 ohms is your final mark for that one. Right, next one. Okay, mass on a spring. Okay, we pull the masses, we extend the spring, calculate the original length. It's just the difference between the two, 3.1 centimeters. Student then removes the masses and notices the spring does not show elastic behavior. That means it does not go back to its original length. Predict a new value. You can't work it out. There's nothing to calculate here. You just have to pick a number that's bigger than 3.1 and smaller than or equal to 14.6. So any number in the range of 3.2 to 14.6 gives you the mark here. Any number at all. Perfectly fine. Right, okay. Now what we do is we set up a little oscillation on it. So we pull it down and we allow the thing to bounce up and down. And we plot a distance time graph between how the distance between this and the support, and we get this kind of curve. Explain how the gradient in the graph shows the masses accelerate as they vibrate. Okay, so what we need to think about is we've got a distance time graph. What can we work out from the distance time graph? We can work out the speed from the gradient. So our first marking point is to say that the gradient is the speed. Is our first marking point. Our gradient is changing. Feels like a very we're changing our gradient over time. So if the gradient, so therefore our speed is changing, so therefore our speed is changing over time. And a change in speed over time is the definition of acceleration. So that's what it is. It's literally make that comment, and therefore make that comment. You don't actually need these. You don't need to say over time. It's not essential, even though that's what it is. And then when do we want to show all the times? And that's key. All the times, not just once. When the masses are not moving. Well, it's any time the gradient is 0. So when it's flat. So it's flat here, 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 and here, because it has to stop and come back. Right, okay. Right, we then have a bit of calculations. We've got a manometer, which is a pressure measurement device. There's a lot of information here, but fundamentally it just comes to we have a height difference and we have therefore after a pressure difference. And for 2 marks, we're literally putting the numbers we're given, 14 density, we've got G, got the height difference, we're just putting them in and we get 13,160. So substituting in, getting the answer, 2 marks. It can round to 13,000 is perfectly fine. Then we have a velocity time graph, and we're asked to show that the distance travelled is 4.7 centimeters. From a velocity time graph, the key thing there is that is the distance is equal to the area under the graph. So we need to use that one. We can't just use speed as distance over time because our speed is not fixed. So it's a triangle, so it's a half times base times height. So it's half times 0.2 times 47. Put our numbers in, work that out, and it comes out as being 4.7. Acceleration, so calculate acceleration. The acceleration is the gradient, which is change in y over change in x. Okay, it's a big triangle, it's already there, so your best bet is to literally use the whole line. Okay, so our gradient is going to be our change in y, 47, over or minus 47 to be perfectly fine. I've missed that out myself. It's actually minus 47 because it's not in the mark scheme, but as a marking point. Sorry, it's minus 47 and there. So minus 47 over 0.2 seconds. So you get minus 235 centimeters per second squared. It doesn't in this mark scheme require you to have that negative sign, but that's not always true. So 1 mark for recognizing this. 1 mark for putting your numbers in, 1 mark for getting the answer. There is no mark for the negative sign. It's easy to forget, but in other exams there has been, and that would make it a 4-mark question, but it is a negative acceleration because we are slowing down. Right, question 10. We've got an investigation, and we're going to start with a few things. Student investigates how the time taken for a ball to roll down a slope changes with the distance from the bottom of the slope. We've got a method, and we want to identify independent, dependent, and control variables. Just as a quick thing to remember, there will only ever be one independent and one dependent variable. So you'll never tick multiples in these, because you can only ever have one of each of these, and then everything else should be a control, or your experiment is not going to show what you want it to show. But yeah, we're changing the distance traveled, we're measuring the time that it takes as a result of that, and we're going to control the surface of the slope and the angle of the slope. We're then given some data, and we're asked to plot it and to draw a best fit curve. There's not many marks for this because they've already drawn the scale and everything. So we get our scale, put our plots, put our points in, and draw a curve through the points. Now they are not interested in this region here, so there are no marks can be lost for if you just had the thing going down there, going straight down. It's only in this region here you should have a curve that's going through all the points. So because they haven't told you that it goes through 0, 0, there's nothing to worry about there. Okay, and then we had this question, which is a sort of a new style of question they haven't asked too many times, is test this relationship. So essentially there are 4 marks for using the student's data to deduce whether the student's results support this conclusion. So the first step you need to do is to take each of these values and essentially do distance divided by this number squared. So that's the first thing that we have to do. And if we do that, and I'll just write down the actual values that you get very, very similar values. You get 59.49. So this would be distance over time. The important thing is the time is squared. It's not distance over time squared, it's distance over time squared. So we then get 59.45, you get 59.51, 59.49, and 60.38, I believe. Now, you get 1 mark for doing any one of them. You get a second mark for doing another one of them. So you have to do at least 2, and then you have to basically make a comment where you are drawing a comparison. Now that's entirely a little bit up to you. To me, I would say, hey, these are pretty much all the same. So I wouldn't be bothered about that. I would say, yeah, these are all essentially the same. These are all essentially the same value. You might, however, have done, say, you might have done this top one and this bottom one, and you might disagree. You might say, no, I think 59.49 and 60.38 are very different numbers. That is in many ways up to you. You can make that's your judgment call. There's no right or wrong. You just have to pick the 2 things. I think it's fair to say that these 2 top ones are essentially the same. If you've done this last one, you might argue that it's not. So there is a sensible comment for 1 mark. Now, it might also be that you've done this equation wrong. Maybe you've done distance divided by time and then squared it, and all of your numbers are very, very, very different. You can make that. Your comment might therefore be, actually, these aren't wrong. You've not got these 2 marks, but you're making a sensible comment based on the things that you've put there. Okay, so even if your constants are not equal, if you comment that your constants are not equal, then you get a mark. And therefore, you say, therefore, your consistent conclusion is, you would say the conclusion is therefore correct or incorrect. So if you've done the calculations correctly, then your sensible comment is that distance over time squared gives you essentially the same number each time. Therefore, the conclusion is correct. And that's how you get all 4 marks. If you've messed up this, so your numbers aren't quite right, your comment could be it's not a constant, and therefore he's incorrect, and you can still get those other 2 marks for doing so. Okay, number 11. So we're all about heat transfer in number 11. So I want to go talk about these a little bit more. So we've got some countries, snow can fall and collect on the ground. You're sitting in international GCSE, and there'll be people who sit this who live in a country where it does not snow. Diagram 1 shows that after the snow has fallen, the sky can be clear, leaving the snow directly exposed to the sun. So we've got snow, we've got ground. Explain why the white snow, and I'm going to highlight the word white because that is the important term in this thing, takes a long time to melt, even though it's directly exposed to the sun. Well, the problem is, how does the sun's energy get to the snow? Well, it's coming through via rays of light, but as we know, snow is white. White reflects light, so the light bounces off again, doesn't really get absorbed. So the argument is that white is a poor absorber of radiation. Okay, and essentially that gets you the 2 marks, making that sort of like thing. So you are making a you're making a reference to absorption or reflection of radiation, and you're linking that to the color of it. So white is a poor absorber of radiation. You can say white is a good reflector of radiation. That's an equivalent statement that also gets you the mark. So you can also say so that is, again, that's an equivalent statement. So they both, again, that would also get you 2 marks. Any indication that we know you're talking about absorption or reflection gives you the mark. If you get it the wrong way round, however, you'd only get 1. Okay, so then got another diagram, and we've got a metal drain cover. Okay, and I'm going to highlight the key word in this sentence, metal. Okay, explain why the snow melts in a shorter time on a metal drain cover. Now, it's got nothing to do with the color of the metal. We're nowhere near radiation. We're interested in metal. What we know about metal is that metal is a good conductor. Okay, so why will landing on the metal melt the snow? When snow falls on the metal, the snow is at freezing point. The metal is definitely not. So the metal is warmer than the snow. Okay. It is a good conductor. So energy can pass quickly from, and this is important to get the direction of this right, okay, the metal is the warmer thing, from the metal to the snow. So the energy is going into the snow from the metal drain cover to melt it. Any 2 of these 3 are the marking points. So any of those 3 will get you the 2 marking points. Explain how a convection current above the snow increases the time taken for the snow to melt. Okay, so I'm going to start off with what we know about convection currents. We know that about convection currents, simple statement, warm air rises. Okay, so the warm air is going to rise. So let's say we've got a little patch, I'm going to colour it in red. Okay, I've got some slightly warm air, warm in comparison to the snow. But the thing is, it's going to go upwards. It's going to leave. Okay, so I'm going to cut it off, and off we go. Off we go. Off to the top. So off to question 10. What therefore is going to replace that warm air? Well, what will replace that warm air? I'm going to write it in blue. Is some cold air. Okay, cold air is going to come in and now sit above the snow. So we've got some cold air. So now, okay, we no longer are in contact with warm air, we're in contact with cold air, and therefore that is going to slow the rate at which energy is transferred. Okay, so energy doesn't transfer as quickly out of the hot thing as it does the cold, as it does the cooler thing. Colder air in nearest the snow. Okay, so we get a layer of cold air sitting on top of the snow, and therefore, because we've got cold air rather than warm air, rate of energy transfer is less. Okay, there's just not as much energy that can pile out of the air into the snow as quickly because there's less energy in the cold air than there is in the hot. Again, you can so this is it's quite tricky bit to get, but you can just say you've got warm air rises leaving cold air next to the snow. That gets you both marks. You can also therefore relate it to the rate of energy transfer. And now we're on to the last question. So we have a LED and a resistor in series with a cell and an ammeter. The voltage across the LED is 0.63 volts. Calculate the current in the circuit, so we want to know what ammeter reads. Give your answer in milliamps. Okay, so we at some point, the key equation we need to use if we want to work out currents and we've got voltages, we want to use the equation V equals IR. But we don't know the resistance of the diode. We can't do that equation for this because the resistance here is unknown. But we do know this resistance. So the first thing we have to use is the fact that voltage is shared because the two things are in series. So if this is 0.63 volts, the voltage that this thing has is 1.5 minus 0.63. So this thing has 1.5 minus 0.63 volts. Okay, now that comes out as being 0.87 volts. We have 0.87 volts around this resistor. That's our first thing that we need to do. That's our first marking point to get this number. We then can take this number and this resistance. So to work out, that's the equation we use. So we're going to put these numbers into our equation. So we can put, so we can put, say, 0.87 is equal to the current times the resistance, which we know is 95. Okay, and now that's our second mark. We can therefore rearrange that, so we divide that through. So our current is equal to 0.87 over 95, and that is going to come out as being 0.00915 amps. Okay, so this first bit is a mark, this is a mark, and this third bit is a mark. So we've got to 3. How do we get that fourth mark? We want the answer in milliamps, so therefore we have to times that by 1,000. So therefore we times that by 1,000 to turn it into milliamps, and we're going to get 9.15 milliamps, or that might round to 9.2. And then we have this last question, which is we add a second LED and an extra resistor connected in parallel with the cell. The resistor and the LED are the same as the components are used in the same as diagram 1. The two resistors are identical, and the two LEDs are identical. Explain how the ammeter reading will change. Now, there is a misconception that happens a lot with this question, is that adding more things must mean that the current goes down. But something that's important, when you add components in parallel, the resistance is less because there's now, as opposed to there just being one route for electricity to go, there are now two. So we can send out electricity down two alternative paths. That means that there is a lower resistance. Okay. So here's what we can say about this, is that the resistance of the circuit is halved. Oh, sorry, I'm going to the end point there. Sorry, it's less because resistance to the circuit is less because an extra path is added. So the overall circuit, that's the whole circuit. If we took it as a whole, extra path, we've got lower resistance. That there is 2 marks. You can get a 3rd mark here for saying it is halved. You can say that in this because they've told you the things are identical. Okay. Now, this is not always true of every time they add stuff in parallel. It's only true if you add things that are identical. So don't remember that as a rote thing to say, but do be aware that if it's an identical branch, then yes, it will halve. So there are 3 marks you can talk about in resistance, but the first 2 are probably the easiest 2 to get. So we can also say, well, what else has happened? Well, the voltage across each branch is still 1.5. There's a common idea that somehow we would split, that would get 0.75 and that gets 0.75. Nope. If I stuck a voltmeter across here, I would get 1.5. If I stuck a voltmeter across here, I would also get 1.5. So that has not changed. So there is another mark that you can get for highlighting that the voltage so you can make that observation. You've got the voltage across each path is 1.5 volts. So, I mean, from this, it's possible to get to this point, and you haven't actually said anything about the current. But essentially, given we've got a lower resistance and a higher voltage, well, if we think back to the equation we've just sort of like had to use to work out current, well, this is going to be voltage divided by resistance. That's how that equation works out. We're going to have a higher current. Okay, so it hasn't told us how it will change. So we've used some logic. We know the resistance is less, so the ammeter reading will increase. So ammeter reading increases, and you can actually link it back because you can actually do a calculation to show if the resistance is halved. Well, you can also actually say that it doubles. Now, the reason for some of these things is that if you say it doubles, you're getting that point, and you're getting that point. So, if you were able to work out that the ammeter reading will double, then you actually get both of those both those marks. There are other ways to argue about it. You can talk about like the way in which the current has flowed and these sort of things, but these are the main key points that are in the mark scheme. But most of the time, the way that people go wrong is thinking, I've added stuff in parallel. What does that do to the resistance? The circuit's resistance must go down in that case. And there we go. That is the Year 11 mock. And I hope if you have any other questions, then do feel free to ask.